Hi, my name is Rodrigo Miller, and I'm going to present this article called An Architecture Proposal for Checkpoint Restore on Stateful Containers. First, I will do a small introduction to the theme and the objectives of this paper, then I'm going directly to the architecture proposal and proof of concepts. Service availability for stateful containers are still an open challenge, because you can't simply replace a faulty container with a new one built from an image obtained on a registry. For example, on a Redis instance running as a container, part of the state is in memory. If you replace the running container for a new one, you lost all this data. Even replace the container can't really guarantee that the service is operational. One way to control this is to use checkpoint restore. With this technique, you take a snapshot of the container periodically. In the future, if you need, you can create a new container of this snapshot. However, unlike hypervisor, doing checkpoint restore is not an easy task from containers, because those are Linux processes and the tools are still under development. Another point is that checkpoint restore is not sufficient to provide strong consistency, because you may have scenarios where there are requests that haven't been saved by the latest snapshot. So, even if you restore this snapshot, some requests would be missing from the internal state and the container wouldn't be consistent. The objectives of this paper is to propose an architecture for a recovery service for a stateful container based on checkpoint restore techniques. Also, a proof of concept is designed for Kubernetes with the creation of a custom resource to manage the container lifecycle inside the Kubernetes. This architecture is based on three big concepts. First, the operator, responsible for controlling the container lifecycles. Then, the interceptor, responsible for both keeping track of the requests delivered to the application and to trigger checkpoint restore tasks. Finally, the state manager, responsible for storing the checkpoint snapshot and metadata. About the operator, he is a controller, maintaining all the replicas in execution and starting new ones if required by launching the recovery procedure. In this proof of concept, the operator extends the Kubernetes stateful set controller. Stateful set is a feature from Kubernetes that generates a unique identifier for each pod, from 0 to n replicas, and also the storage is bounded to this identifier. So, even if the pod crashes, a new one will assume this place with the same ID using the same storage as the previous one. The interceptor implements the ambassador pattern and acts as a sidecar, intercepting all the requests issued to the application. Using this approach has the advantage of, while the application is frozen to the snapshot generation, this is transparent to the client, because the interceptor still receives the request storing on the buffer. Here we have a message diagram. The process begins with the client sending the request, then the interceptor stores it on an in-memory buffer before sending the request to the application, where it is processed and the response is sent to the interceptor. Then the interceptor marks the request as processed and sends the answer to the client. The state manager stores the metadata containing information like the integrity of the checkpoint, version, and the recovery point from the snapshot. This data is stored on the proof of concept using etcd, a key value database already present on Kubernetes. The snapshot is stored on any persistent volume available. Using these tools, we ensure strong consistency and high availability. As I said previously, the interceptor is responsible for triggering the checkpoint routine. On the proof of concept, the tool crew was used to perform this task. On this message diagram, we can see that after saving the checkpoint snapshot, we can dispose all the requests from buffers. All the requests marked as processed. With this, we avoid making the buffer too large. The operator can trigger a container restoration when new instances of the application are being deployed or when a crash is detected. This detection is made by the interceptor using the circuit break pattern. The interceptor continually verifies if the application is running using heartbeat messages. If the interceptor doesn't receive response from this heartbeat, the circuit breaker trips, and the interceptor only transmits some request to the application, storing all the others. If those requests are successful, the interceptor resumes the normal operation. Otherwise, the interceptor informs the operator that the container is not responding by destroying it. When the operator detects that the number of running containers are smaller than the required, it will start a new deployment from the latest snapshot available. It's important to note that the application is considered a black box to the interceptor. So, if some requester fails, and the container is restored, and if the same request are issued again, the container will crash again. There is no treatment to remove faulty requests from the buffer. Talking about trade-offs and open challenge, we assume a crash failure model, where both the application containers and the interceptor may fail. If the interceptor fails, the operator destroys the pod containing the faulty interceptor. If the application containers fail, the recovery protocol is triggered, as we discussed on the previous slides. In both cases, the operator will put the faulty pods down and launch the recovery procedure to activate another replica. Also, this proof of concept uses the Kubernetes native self-healing. As discussed, only detects if the container is down. To improve the detection of some erratic states or particular threats, application-specific health checking procedures would be necessary, but those weren't covered by this proof of concept. One improvement of this architecture would be using a proactive recovery protocol. By having a quorum of correct replicas, the interceptors plugs on those replicas could compute the correct replies and identify which replicas diverge from the majority, forcing the recovery of those replicas. Another point is that we use an in-memory buffer to store the requests. Frequent checkpoint truncate the buffer, reducing the number of requests to be re-executed. However, those checkpoints cause temporary freezing while the snapshot is being saved. Alternatively, sparse checkpoints require larger buffer, but the time to replay all the pending requests is higher. Also, on catastrophic scenarios where all replicas fail, the buffer content must be saved on stable storage. To avoid this cost, one alternative would be use reactive checkpoint restore, only save the application state when requested by a recovery replica. On the scenarios when the container fails, the operator asks for a checkpoint from any available replica. This replica saves information about incoming requests and generates the snapshot. Using this approach, a lower overhead is expected, but the recovery time is higher. Also, this approach assumes a crash failure model and tolerates only F failures for a system with F+1 replicas. Concluding this presentation, guarantee high availability and strong consistency is still an open challenge for stateful containers. The checkpoint restore technique appears to be the main strategy for container migrations, but can ensure consistent recovery by itself. Therefore, we extended the checkpoint restore with an architecture which allows to fully restore the stateful container. This architecture uses widely accepted patterns like sidecar containers, operators, and circuit breakers. Finally, the following steps include a performance assessment of this architecture, because as we intercept the request and the application freezes due to snapshot, it is expected a costly overhead. Thank you for your attention, and we are open to questions.